Bridget, are you drinking tea? Okay, yes. I think people will join us as we proceed along. And good morning to you all. We are in an unusual platform today. Blackboard Ultra is not responding. So I had to switch to Zoom. If you have been subscribed to it, like myself, you know, Zoom can only give you 40 minutes. So we don't have that much time for it. I just hope you are busy with, you're already busy with the rehearsal exercise which I gave you for your labs. So today's class, I will be continuing that work in a theoretical basis. We're gonna look at passive networks, and then we check the transfer function for passive networks. That's all we do. And then from there, as far as transfer functions are concerned, we will be done. So, and whilst people are still joining, perhaps let's talk about how your prac gonna be. That will be a practical, like I said in that presentation for your simulation, that a practical is like a test. It's gonna be like a test. I will give you different resistor values online, of course. And then from there you will simulate. So your result won't be similar to your friend. And then you submit within 1.5 hours, like a test. And then thereafter, you carry on with the results and to finalize the report, which you're gonna submit as an assignment. So the practical will have two things: a test, which you submit within 1.5 hours, and then a report, which comes as an assignment, which you submit later on. So I don't know if you are clear with that, but then the date for it, we're gonna just jump next week, and then that Monday after next week is gonna be your prep test. And then let's talk again about the tutorial which I sent. It was hectic. I saw it yesterday when I compiled the memo, but simple in a sense that those answers, every answer for that tutorial is there somewhere online, hidden somewhere online. So I was testing you if you are able to do research using online tools and get the answer. What I would not like is for you to, after getting the answer, you copy and paste. You know, I hate that. You have to rephrase it in your own way, words. Make sure you understand what is being explained. So it was pushing you to study. So how are we gonna mark that? It's very simple. We look at your work. It's yes or no. Yes, if you have done it and you didn't do copy and paste. No, if you haven't done it and you have done copy and paste. So if we decide on using that, it's not every tutorial that we're gonna use. If we decide on using the mark from the tutorial, it means if we decide to use the mark from the tutorial, it will mean that if you did it, we can just give you a certain mark, and then that's it. If you didn't do it, no mark. So it's not that we're gonna pinpoint and say this is what you should have got, this is what you are coming up with. All right, guys, listen, it's Zoom now. Let's start with our work. Any quick question? Don't raise hand, ask. Unmute yourself and ask. Well, you also do this on Zoom. I thought Zoom is gonna be better. Right, you don't like talking. All right, fine. Let's do today's work. I'm gonna share the screen now with you. Now, at least answer this one. Are you able to see my screen? Yes or no?
Yes, sir.
Yes, we are able to see the screen.
Okay, thanks a lot. Let's move on with it. You know what? I just realized yesterday that is there any person in this world just to ask student this kind of questions? These things look so simple. Maybe if you look at it in a wrong approach, I'm talking about the circuits which you were simulating. It looks very simple, but yes, perhaps it's simple if you do it the way I do it, which uh, perhaps we need to look at other ways, but uh, it's unbelievable. All right. Now, our government now have opened up the eased lockdown restrictions. So if you need to, there is a need for us to meet. There's my office number. Make an appointment using this number, right? And then if necessary, we can meet. But don't just jump to that, guys. It's nice for you to sit at the comfort of your homes and we do this thing, and because COVID is not gone after all. Mute yourself there. Now we're carrying on with transfer function, but now we're going to look at passive. In that simulation presentation, I explained to you that we refer to passive things which don't have to be biased, things which doesn't have VCC and ground for them to work, like a resistor, like an inductor, like a capacitor. So with this, we're gonna show you how you can model RLC circuit. And again, it's still we're carrying on with our motive to demonstrate the significance of control system engineering in electrical in particular. Remember, control can be used in business, can be used in mechanical, can be used in industrial. So we are aligning it to where you are in, to give you more appetite about this subject. Now, these are the components under RLC circuit. You've got the resistor, you've got an inductor, you've got a capacitor. That can have a voltage across them. And then you have a current which passes through at any time. Now, if we make our output a current for us to get transconductance. So for our transfer function, we're looking at I over V. This is your equation, right? And then this is an equation for the current through an inductor. This is an equation for the current through the capacitor. Now, when you can, like, if you try, you can convert this to, or analyze that, or get the transfer function using Laplace transform. It's said it's much more easier to work that way. Then you introduce that variable P or what, or S, right, to show that you are on the S domain or P domain. So, but then if you take this, you make V the subject of the formula. V will be equals to IR, for instance, and then the Laplace, it will be V of P is equals to I of P of that. So that's the thing. And then when you come of this is gonna take you like an inverse of 1 over LP V of T. And then this one, CP V of T. So you've got the table next door on the next slide, which summarizes the transfer function as represented when you use Laplace transform. Remember, it's our choice here to make current the output. We could have made the voltage as an output. So as for impedance. Right, so there is a summary for a capacitor, and it goes with its row, which go to your right, and you look at if the voltage is an input, the current is an output. That's your equation. Now you see now, if the current was an input, you were not integrating. It was not an inverse of Laplace. You had it straight away. and there was no reciprocal there. But now once you move to voltage, this becomes the opposite of one another. So switching from voltage to current, here you can see it clear. The inductor here, where you make current, you invert. But the capacitor, you don't invert. But where you make voltage, you invert for voltage. You don't invert for the inductor. So no, you don't invert for the inductor. Yes, of course, they didn't invert. So this is how it works, right? So this is a summary of everything. Most importantly, if you look at the transfer equation in terms of admittance, that's when the current is the output. Then you have CS for the cap, and you have 1 over R as a transfer function for the resistor, and you have 1 over LS as a transfer function for the inductor. So that it is where how your transfer function is built. If you make it the opposite, which is voltage over current impedance, what you are used to, then the poor capacitor will be inverted. Right. Now, it's quite interesting to look at this. That's when I say this thing becomes simple. I said last time, if you can look at this and look at it as omega, then you are thinking you are out of Laplace. You can be working the values of impedance the way you were taught in a previous subject, that 1 over WC is a capacitive reactance and WL is a inductive reactance. So note that. So you can move between, use where there's S, you put W, and you start doing things, making things easier. Right, now we've got an example to clarify that. We've got V in and V out. Now, the gain of this, the transfer of this is V out over V in. Right, now, I want you to forget about Laplace. We think about the impedance. Remember, V out over V in, you've done that in electronics somewhere. I'm not good with the subjects, guys. I'm from old school. We did those things, S1, S2, S3. I don't know what they do with you in BH Tech. I've been teaching on honors level and master's level, so they just call me, come and help the guys on BH Tech. So now, I'm not familiar with what you did before, so don't take chances. I will ask my colleague. So you know that V out over V in is equal to ZE out over ZE, lower level electronics. Now, what we need to do is to calculate Z out, right? Write a formula for Z out. Where is the output? It's taken across the cap. So this output is seeing the impedance there of that cap. Right, then from there, we take a reciprocal of C multiplied by omega. That will be Z out. What about poor Z in? When you look that way, you see from there, you've got this one, R in series with the cap there. So, right, that formula we already have, 1 over WC and omega C. We just have to add the value of R to it for Z in. And then we substitute on that equation of Z out over Z in. Then we have 1, that's for Z out, it comes there. And then that one, it goes to the bottom. We simplify by multiplying by omega C on top and at the bottom. We remain with 1 on top. If you multiply by the omega C there, you will have this cancel. And then we have 1 over 1, 1. And then you multiply by WC there, this one will be cancelled and form 1. That one are WC. So now, I said I gave you a hint there. You just, if you're gonna switch to the Laplace domain, you go there, you put P for omega, and that will be what you could have as if you use the Laplace transform. That's it. That's what the kind of things which you can also get in your labs. You already saw on my demo video. That thing, keep on watching it, guys, and do it yourself. If you've got problem, I asked you if you've got problems, but no one said, I don't have multi-C. Where do I get multi-C? I don't know. That's your baby now. Let's carry on with the work. Now, if you wanted to do Laplace, then if you write those nice equations, that table which you have, I don't want to go back to that table. Right there, for VI, you're going to produce VI with I and R. Remember that they are using the S. S is where you had P. I use P myself. So that S is the same thing as P. R, I of P, R, I of P. That's a Laplace transform over the resistor. And then remember, we are using a voltage, and then from there, we take a reciprocal, inverse Laplace capacitor over a Laplace domain. That is your input. It's on the resistor and the capacitor. You remember that diagram? We had the resistor and the capacitor. Capacitor, resistor. So they were together. But what about the output? It was only on the cap. So this part of the equation. So you divide. Oh, V out of and that. Guys, and then from there, you do those fancy things, simplify. To me, this one, it has got a lot of text. It doesn't look simple. But anyway, that's you get the same result with what you get. And this one is going to be your P. Right, there where we had a P. So you could have done the same. That's where you have your S now. And then that's what, so that's PCS and that's RCS. So P is replaced by S. So PRC, and then you add SRC. I don't know where you read it from, but ultimately this is what you are getting. SRC is just the order of alphabet there. I wouldn't mind about the order where maybe let's stick to this one. We normally said RLC, so that C must come after R. And then from there, we put our P like they did there. So, but I won't like somehow harm you for shifting around that order. I'll be able to understand what you are doing. Right, so we take a next example. We see now we have RLC. So that's the order we just like adopted now. Everything is there, full house. I will be grateful to have you attending that way. Everyone come to my classes. So there is your input as you look from that side. And then there's your output is only at the cap, no stress. So your output is that at the cap, omega C. Then the input is the sum of everything. You want to ask a question or just joining in, right?
We can't see the slides anymore, sir.
Oh, you stopped seeing it.
Yeah.
Let me just restart the presentation. Thanks a lot. For how long now? Only now?
Yes, only now.
We only see a Google screen, sir.
Okay, let me just go out now and then come back to the presentation. All right, are you seeing my screen now?
Yes, we can see the screen. Yeah.
I think it's an issue of resolutions. Are you seeing my back now? Can you see the second?
Yes, we can.
Oh, okay.
Yes, sir.
Yeah, it's an issue of resolution. It's like it depends on the setting. We can't go back and change the setting of the resolution. After all, I won't even know which one will be up. Just tell me, notify me if you come across the same thing again. Anyway, we're almost done. So that is your next problem, and then which I was busy showing you that as far as the input is concerned, we're gonna have everything, RLC. So that's for ZI, you consider everything. Your normal engineering equation for RLC second. For the output, you only consider it's across C, and then you consider that. And then you take the ratio of the two, Z out to Z in, that's it, that's it. You multiply by WC, and then from there it will translate. There you already had WL. So it will be W squared CL. That's one thing to note. And then that will be WC, and that one will simply be cancelled. You're left with 1. So it goes to there. And then I just said this should be RC, V out over V in, and then you start putting your S there for this omega. There is what you have. And it's the same thing that you could have seen when you use Laplace transform. Are we still flowing together with the screen?
Yes, sir.
Yes, sir.
Sure. Right. So now we have the same circuit. It's just a copy to that one. But from the word go, we're going to use transfer function. So EI, and then as the equation is there, which we still have to make it, we convert it onto Laplace transform. Then we've got S domain, and then it becomes there. Same thing for out at the capacitor, make it at the Laplace domain, we've got that. And then we take the ratio of the two, and then from there we simplify, and then we have it. So we are doing things two ways here, with Laplace, without Laplace. The question comes, do we really need Laplace transformation to work out Z out over ZE? I think, of course, you need it. You need it because things might even go complicated as we go on. And then from there, you don't know how to model those things without using equation, right? So, but I will tell you which approach to use. If I don't, then use whatever you are comfortable with. But after all, your final result, express it as in the Laplace domain, right? So even if you were using omega there, it means then from there at your final answer, you need to change that. There is something which I used to enjoy. You know, those things when they give you an equation that they say from first principle, prove or derive this equation. And then I don't know what to do. That's way back when I was doing S4. And then I just take that equation, the result which they give me, or say derive it. And then you try to work backward, and then you say these were my inputs. Right, but those were the tricks. It might be difficult now. So that it is now, you can do it, you do it without Laplace, how I relate to my analogy. Then finally, you substitute for omega with S or P, and then you say, yes, that's what it could have been. I haven't seen anything which stops you from that. So I've got something for you to try. We're still together. Screen.
Yes.
Right, thank you. So you can go and try this one and see if you can do it. But look at this now. We are not talking about voltage. We are talking about the current source. You know the current divider rule. So you have to work out impedance. This is going to be your input, and that's going to be output. But in terms of current, perhaps that's where you might realize that if without using Laplace, it's difficult. I'm not sure. I haven't done this one. So go do it yourself. It's suitable for your level. And then from there, we will discuss the answers later on. And this one is the way you did it. That's a voltage source. You can do that as well. And then you see. This kind of circuits, what are they? Like this one, for instance. What kind of circuit are you seeing there? If someone said, name that circuit, what will you tell you? Anyone? You mean we can just join the caps and the resistors and then without the peoples? What is this circuit? What sort of frequencies will pass here? What frequency do you think will pass here? You have an inductor and an inductor. Inductor passes higher frequency or lower frequency? it passes lower frequency, which can't be shorted by the curve. So what kind of frequency, what will you say about this second? Low pass what?
Filter.
Yeah, right. That's a low pass filter. So you can analyze your filter using get the transfer function for filters using Laplace transform and then using this method in control system. So that's it as far as the transfer functions are, guys. Maybe for your lab, I can give you this. A circuit like this. And then I make this one variable, a potentiometer. Then for you to use different things, let's say your student number. It's funny, I don't remember my PhD student number, but I remember my diploma student number. So that was my student number, 9221182. Right. So now, if I'm gonna say, what value do you use then? In kilo ohms, I can say in kilo ohms. You take the last 2 digits of your student number, you add them together. They will give you a value between, what will be the highest? 18, 9 and 9. So any value between 1 and 18. So if this one, in my case, it add to 10, and then I would say it's 10K. So with that student number, you use the variable resistor of 10K. So your port will depend on your student number. That's how I'm gonna make you do different things. I said, use a potentiometer of 10K if your student number, you'll add the last 2 digits. And then from there, that will be your value of your potentiometer. Then you're gonna come up with different things. On some occasion, yes, maybe you won't even know unless you go to the class list who has got the similar values with to exchange with. And then from there, I ask you to start apply DC and then increase this in the steps of 10 and plot the gain for each value. Apply AC and then plot the gain for each value. That's all. And then from there, you make a table. This is DC, V in, V out, again, V in, V out. And without this thing, put a multimeter to measure resistance, measure there, and measure here, work out the gain. So those are the things. But the key thing now, which I want you to bear in mind, don't forget, that's how it's gonna come. Your last 2 digits of your student number is the one which gonna form you, give you the variable resistance. So you will vary it in percentage. So you're gonna come up with different answers. Of course. So that is the trick which I'm gonna use. It's no longer a trick because I told you. So that's the strategy which I'm gonna use. I'm not sure. Are there any questions with regards to the lab, regards to the tab? Maybe one of your questions before you even ask it is, when are you getting your script for your retest? You are waiting for it. Guys, we just came back now. We could not do it over the holidays. So next week we'll try and finish it. Hopefully that will come before your test too. You are almost ready for the second test with this. Well, if you want more tutorial, we can pump it to you. But I don't see any difficulty here in working Z out over Z in. Two-way, use Laplace, not using Laplace. I don't see anything challenging. You're gonna even emphasize the knowledge to you with the tutorial. Guys, any question? Any question?
Is the memo for the last tutorial on Blackboard?
That's a good one. I know that the memo for the last question is online. I said each and every answer that you can get online. I didn't change anything. I just copied questions online the way they are. And you can, like, if you sit down and then you check, you will be able to get those things. So if you really want to get that, you just have to go back online. But yes, it's a good question. The tutors tomorrow, they will discuss the answers with you. You mean tutorial 2, isn't it?
Yes.
Yeah, the tutors will be with you tomorrow. I won't be in tomorrow. I'm giving them some space. I might join you, but it's not it won't be like my class. So the tutors will do that. At some point, you don't have to be with me. You were with me on Monday, you're with me today. So I need to give the other people some question to ask. Well, if you see me not joining in, you can even say something which you don't like about me. They won't tell me. Right. Any other question? Okay. WhatsApp, it's open. So you can like carry on with any other questions which you like to know. But carry on, guys. The multi-sim. Make sure you have a multi-sim and rehearse. And then so that I will give you more rehearsal exercise. Okay. See you on Monday or tomorrow. Bye-bye.
Bye, sir.
Bye.